going to start. First of all, I want to thank you for attending. I think we're going to have a few more people stopping in a few minutes. But my name is Michael Poloyan. I've been involved in the rotational molding industry for at least 20 years and designed products throughout that period of time. My involvement in the rotational molding industry is primarily in design. And throughout that time, I've designed a number of products, rotationally molded products, quite a wide range of products. And what I plan on doing today is sharing with you some of the considerations that I believe should be taken into account when you're designing a product. You know, a lot of times I meet individuals and companies, and they have the misconception that design is essentially sitting down at the computer and doing CAD work, and they think that that's the design. And it's such a false perception of what design is all about. A matter of fact, I've seen so many products that are designed with that kind of a perception, and they're a disaster. So what I want to do is I want to cover many of the considerations that have to be taken into account when you're developing a product. And I call this an advanced course because I'm not going to go over the basic design fundamentals for rotational molding. How many of you in the group here are designers? 1, 2, 3. Okay. Well, you get 3. And the rest, I assume, are processors, or what's the, yeah? Okay. So, I assume that you are experienced in designing rotation molded parts, correct? Yeah, all right. So what I'm going to cover are some of the other things that you may or may not have considered when you're designing a product. Hopefully, and by the way, this is not a professorial type of a presentation. I want this to be casual and interactive. So if you have questions as I go along, if you disagree with anything I say, make it interesting and raise your hand and challenge me, because it makes it more interesting. People won't fall asleep. Okay. So an overview of the seminar is essentially I want to start with the conception of an idea. All right. Now, so you have an idea, or you're presented with an idea, and you have to now transform that into something. And in that transformation, I don't know how you work, but it's always, I find people sometimes latch on to a preconceived concept, and they don't want to part with it. I try to work in a different way, and I think the more ideas you can come up with, the better it is, because a lot of times, once you start coming up with concepts, you're imposing or introducing potential problems because you have to overcome the very things that you're creating. So the foundation of that concept is critical to your overall activities. Everything from that moment of time when you come up with a concept through all the stages of development are precipitated from that initial concept. So you want to make sure that that premise is valid, okay, and I'm going to talk about that. Then you're going to transform that into a functional production design. And that's where you start to include a lot of the design parameters for the process, whether it's rotational molding or injection molding or whatever process you're using to manufacture your product. You have to understand the process. And that's critical. You know, I can't emphasize the importance. I mean, I'm still learning. You know, when I talk to different molders and I see different methods of how they process materials, how they perform the secondary operations, I'm always, you know, enlightened, and I use that in my arsenal of thought process to come up with better designs. Then, of course, there's a production follow-up. Now, I have a consulting firm, and I don't believe that you should, as a designer, just design something and then toss the design over to the manufacturing guy and say, okay, here, I'm a genius, I figured it out, now you guys have to make it. Bad way to work. I'm a firm believer in having a partnership with the molder and making sure that he or she are in agreement with your intentions so that they can consistently manufacture quality products cost effectively and easily. Because, you know, to me, if you're imposing unrealistic restrictions on a molder, you're never going to get a good product, and it's going to be a blame game. So I'm a firm believer in partnerships. And then there's this last detail of testing and validation. So you can design something, you can process it and mold it effectively, but without having valid testing, you may end up with some surprises that you never expected. And that's a key part, because the worst thing you want to face, I mean, having a problem emerge immediately is a blessing. Having a problem emerge after 6 months or a year is a horror show. And see, John's laughing because I'm sure he's experienced some of these things with some of his customers. So you want to make sure that the test, and this is not trivial, because just the testing alone is critical. The parameters that you establish have to account for the possible conditions that that product is going to face when it's in the field. And sometimes they're very difficult to pinpoint. You know, I was just talking to somebody the other day, last night, and he told me somebody, one of his customers or some manufacturer he knew, they developed a paddle boat, and they were selling it in Europe, I guess. And they had a problem where people were paddling out in the water and they couldn't get back. And the wind was blowing them out to the ocean. So they had to stop manufacturing and abandon the whole product. So they invested all this money and time in developing something. So they didn't account for the, you know, what seems to be obvious. You know, you might think about it being an obvious problem, but it's obvious after, you know, hindsight's no sight. So you really have to have the foresight to anticipate what could go wrong. And that's not an easy thing to do. You have to play, you have to be open-minded and not in love with your design, and test it so that before, with a number of people that are much smarter than you in their own area of expertise, so that when you release the product, it's been validated, at least from an overall perspective, from safety, performance. You know, there are a number of parameters that you have to establish, so that's really critical. And then, of course, there's the production release with the part drawings, etc. So I assume most of you, or all of you, have these basic fundamentals, which I'm not going to go over, by the way, because this is an advanced course. I'm not going to talk about draft angles and kiss-offs. I assume you know what these terms are and what they mean. But I am going to discuss these in an application later on, okay? So when you begin with an idea, okay, and I use the word idea because I'm from New York, I say idea. You're supposed to say, how do you say it in English? I don't know. So you begin with an idea, and then sometimes they're a little bizarre. And so it's good to be creative and think out of the box. I'm a firm believer in that. And you discuss your concepts or ideas with associates in the company, come up with sketches. Sometimes you'll have a very crude prototype or model. It doesn't matter. It could be a portion of a product, it could be the complete thing. So you're coming up with concepts for what this idea is all about, and then you establish specifications. This is critical. And without identifying the product performance criteria, you're starting off on a wrong. It's amazing how many companies, I'm talking about established companies, start projects with no specs. It seems bizarre, but the majority of companies will develop a product with no specifications. And I think in many cases, the specs might, and sometimes the specs are slanted toward the company's expertise. So if they're a manufacturer of electronic components or medical products, they might specify that aspect of the product's performance. They don't know anything about plastics or, you know, product design. So they'll omit those things. So you, as a designer, especially in a plastics arena, I believe you as a designer is responsible for establishing the specs, and this is, again, thinking with foresight, okay? Anticipating how would the product be used, and more importantly, how could the product be misused, and what environments is it going to be subjected to, and what materials should you specify, and how does the material have to behave in short and long-term conditions. So, so in addition to that, you get the marketing requirements, okay? So you get the functional requirements as an engineer, but as an overall product designer, I don't know if you work with industrial designers or not. How many of you work with industrial designers? Nobody? Oh, one back there? Okay. Are you an industrial designer? So industrial designers, which I'll talk about a little bit in a few more slides, they're really focused on the marketing aspects of the product and the user, from a user perspective. The user needs, their requirements, the aesthetics, okay, product branding. These things may seem totally, you know, I don't know, some of you may find this to be esoteric or not very important as an engineer, but they're extremely important to the overall company's success in a marketplace. There are human factors. If it's not easy to use, if it's not safe, it's not really going to be a viable product. There's the color and graphics. All these things, and then there's product details, okay? All these parameters are extremely important to get that product out in the market and have a presence and have a value conveyed to the prospective buyer, and that's critical. And I'm using this image of a kayak because I saw this at a show not too long ago, and I was really impressed with the details and all these things that I just mentioned, okay, which they spend a lot of time detailing, okay? And then, of course, there's the cost. And the cost versus the features is an important consideration because that trade-off is really what provides value, okay? So if the product has too many features and it's very costly, but it doesn't really, it's not really, there's no real perceived, there's no benefit to the customer because it's too expensive, it's not going to sell well. And that happens sometimes. So you have to balance that. And from an engineering standpoint, you've got material selection, okay? And that's a critical step. Understanding materials, understanding, at least have a general understanding of how plastics behave. They're very different, they behave very differently than metals. And they, you know, one of the, of course, significant differences between plastics and metals, I mean, there's no comparison, but one of the significant ones is the thermal conditions. So plastics tend to change properties significantly with temperature, so you have to take that into account, right? Then there's the overall structural requirements and the product life. There's the ease of assembly, defining the limitations of how that product has to perform, understanding the environmental influences, thermal, UV, electrical. There are a number of considerations, environmental, chemical. There's the ease of molding, okay? So that's really, when you get into the ease of molding and how it's designed to be easily manufactured, now you're getting into that list that I showed you earlier of all this design consideration for rotation and molding. You see that in the handbook. And then there's the overall function of the product. And in many products, especially today, there are some stringent safety requirements and regulatory compliance parameters that you have to contend with. And if you ignore those, you can't sell a product. So you have to be aware of these things, all right? And all these things all these parameters, in my opinion, are in the domain of a designer. If you ignore them, you're going to end up with problems that have to be solved all the way down the line. So, in the realm of product design, there's typically two domains. One being that of the industrial designer and the other one being the engineer. They've been, I see them as one continual development, but for many companies, they're two distinctly different disciplines. And based on your education, they are very different. I happen to play both roles, both an industrial designer and an engineer, because that's my background. But the thought process is quite a bit different. Industrial designers tend to focus on the okay, I'm going to start because I want to make the most of the time on here and give you guys the best value for your attendance. So when you're designing a mold, a part for taking into consideration the tool design, it's important that you are aware of the implications of your features that you're adding. For instance, if you're adding undercuts, you have to make sure that you're visualizing how that part, that loose piece in the tool is going to be pulled and how it's going to be actuated. If you don't think about that and just do it blindly, you could end up running into problems. I can't get into details about it, but I'm just making you aware that understanding, first of all, to run the draft in the proper direction of the pull is an important consideration. You want to make sure that there are no obstacles that you could no features you can put in your design that could inadvertently affect the way that side pull is actuated. And you might even want to talk to the tool maker in terms of how the side pull is going to be engineered, because sometimes they put it, for rotor molding, they sometimes put it on rails so that it slides in and out repeatedly, easily. Sometimes they're just loose pieces that come off. So it's important to understand that, because it will affect the part design. And you don't want to put features in a tool that really can't be easily moldable. I'll leave it at that. The application of draft is important, because when you're designing a part, okay, there are many instances, and this is why it's good to, of course, every time I walk over here, I leave a pen over there, and I'm running out of pen. Hold on. All right. So, I'll give you a good example. This is a very simple example, but it's really a classic one, okay? If you're designing a part, okay, let's say you have a double wall section. This is a wall A, wall B, and an outer wall, inner wall, okay? And you're gonna mold a hole, all right, through here. Now, and I'm gonna show you an example later on in the actual case study. You could run it from one side of the tool, so you could core it from the bottom, in which case the draft is going to run this way. Or you could core it from the top, in which case the draft is going to run in the other direction. So, a very simple thing, but it could end up introducing complexities for the tool maker. So, it's always good to talk to the mold maker to, at some point during your design, to make sure that the way you're running draft is not going to cause undue complexity for the guy making a mold. So that's it's an insignificantly simple example, but it gets more complicated. Sometimes the core and cavity can be, the parting lines can be quite complex, and you really want to talk to the tool maker to make sure that he's in agreement with what you're proposing. Another important consideration is parting lines that are running parallel to draw, meaning here's your mold, okay, and it's opening like that. If you have a parting line that's running up this wall, okay, and you design it so that the feature, let's say the feature looks like this, okay, and you design this with no draft, all right, this is not a good example. Let's say it's a hole. Okay, it's a better example. So let's say you're molding a hole through this piece right here. So you have a piece of metal coming up to mold the hole. And then you have another piece of metal coming down. That's called a kiss-off, okay? If you don't have enough draft on this surface, and this guy's going to relate to it 100% because he makes tools. If you don't have enough draft on here, you're gonna get galling. The mold's gonna get all scratched up. So if it's 0 degrees, forget it. You're gonna get all kinds of problems. Nobody's gonna wanna even mold it anyway. So if you have conventional 1 degree, you will still get galling because the angle is so slight that the metal will just eventually wear and tear. So typically, when you have features like these, like that bypass, you want to have a minimum of 3. A lot of molders don't like that, but that's what I kind of use as a minimum. Or 5 or 10. The bigger the angle, the happier they are. So if you get away with it and you want to put 10 or 15 degrees draft on that wall, they're happy campers. But a minimum is 3 degrees. So just keep that in mind. So these are the little incidental things to keep in mind when and I'll show you an example in a few more slides when I get into the case study. That's what I mean by understanding parting lines. And another thing to consider, because parting lines with rotational molding, with the cast tools, at one time they were all kind of hand massaged to get all the parting, all the surfaces to match up. Today with the CNC machining, they're right on the money. It's like an injection mold. I mean, I've seen injection molded parts and you can't even see the parting line. That's not really true with with the rotational molding, but the CNC tools have really, improved the parting line quality. But again, you get wear and tear on the tools and those parting lines become more evident with time. So when you're designing something, you want to make sure that the location of those parting lines is ideally not going to be on a major visible surface, okay? Another important consideration that you may not find in, I think somebody's asking me about the design manual for rotational molding. You might not see it too much in there. There's something that I didn't really consider when I first started designing rotational molded parts, and that's this thing called bulk density, okay? And it's interesting because it's totally unique to the process, because polyethylene, the form of the polyethylene that you're molding is a powder, unlike injection molding where you have pellets. So the powder has a much lower bulk density than the pellets because it's fluffy. So when you're designing a part, and I've run into this many times, especially if it's a fairly complex geometry, the volume in a mold may not be sufficient to hold the powder that you need to get the wall stock that you need. So you have to be careful, and I'm going to show you how to figure this out. You have to take that into consideration, and it's not just a blind, simple mathematical correlation. You don't just go, okay, here's the bulk density, which is typically 1/3 of the material's base density. So polyethylene has a density of about, what, 0.925 or something, depends on the resin. Very decimal places, it varies. But, so if your bulk density, the bulk density is usually about 0.3, it's about 1/3. It's somewhere in that range. I usually use 1/3, that's a good general number, okay? So that means you need 3 times the powder in terms of volume to get the desired wall thickness that you want. And it could really add up quite readily. So you have to take that, I'll talk about it in the next few slides. And then you need heat distribution. You got to also take into account heat distribution. It's not like an injection mold where you just, ramming material into a cavity under high pressure, typically about 40,000 psi. Here you get gravity kind of sort of melting this powder on the surface of a mold. And depending on the heat distribution, which can vary significantly with the part geometry, what I mean by that is it can be expressed quite readily with an image, which I'm going to show you shortly. So let's assume you have a feature in a part like this, okay? So here's your part, okay? And if I could only remember, hold on to these things, okay. So here's your part, and here's your mold right here, okay. So you've got a shell mold with rotor mold, right? Typically 1/4 inch to 3 inch wall, right? This is aluminum. So now this is tumbling around in an oven. And this surface is going to get heated quite readily. But you're not necessarily going to get that much heat down in there. It's kind of trapped air. Okay, the air's not going to flow in because you're relying on a hot, convection heating, right? So the air's not going to penetrate down. So sometimes they put heat sinks on here to suck the heat down there. Sometimes they use a Venturi to blow hot air into those crevices. But if you don't get sufficient heat in these little valleys, you're going to end up getting a thin wall, and I've run into that. So what happens is you either get a thin wall, or you overheat the resin to compensate, and you end up degrading the resin, and you end up with a failure. There was many years ago, I designed a diesel tank. And it was a pretty innovative design. It was a diesel tank, and I had an arm-twisting argument with the molder. Okay, we were like we had a tug-of-war argument going on. So it looked like this. This was a tank, and it's not my presentation, but I'll just show you. Okay, it was a 100-liter diesel tank, and fuel tanks, they have barriers in them to prevent the fuel from sloshing around. So sometimes people, I don't know how they do it, but I've heard of people putting polyethylene or some sheet in there, and they fuse it into the wall. I think that's a pretty lousy way to do it. So I wanted to mold it in. So how do you mold a barrier into a hollow tank without adding something like this? What I did was I designed these cores. So the cores came in from 4 sides. I've seen people copy this already. So you got a core this way, a core that way. This is a line to draw, and that's a line to draw. Here's the party ones. I don't know, somewhere along here. Okay. So these two were side actions, and this was, in the tool. So these things form this. It looked like a Maltese cross. This barrier that looked like this. Okay. And that essentially abated the fuel from sloshing around. Okay, that became my barrier. The problem was I had to keep these relatively narrow because the dimensions of the tank were limited. I couldn't make the thing infinitely large. I had to work within certain restrictions. And the volume, of course, had to be 100 liters. So when you start doing all the arithmetic, what's left is what you have to deal with, right? So I'm taking away material by adding this dead space, okay? I'm losing volume. So I left this at about 2 inches, and it was fairly deep. It was about, 8 inches deep per side. So when I started rotomolding the parts, it was cross-linked polyethylene. They couldn't get the heat down in there, and they ended up insulating the mold with fiberglass and doing all this other stuff, and nothing worked. So I'll tell you what the solution was. But in any case, when they did a drop test, and they dropped this thing from 30 feet onto concrete, it looked like an egg, just splattered all over the place. Because the wall section through here was paper thin. It was about 90 thousandths. It was supposed to be like a 3/8 of an inch. So plus it was degraded. It was overheated. All right. I don't like to use the word cook, and I like to use the word cured, because the plastic is not cured. Cured is for thermosets. It's basically fused. So the plastic was basically degraded and too thin, and it had no impact strength. So the guy that I was working with, another gentleman, he ended up building Venturis to dump heat into those cavities, and the wall section went right back up to 3/8, and the thing worked like a charm. They were able to drop it from the freaking Eiffel Tower, and it didn't break. So I'm exaggerating. So in any case, understanding heat distribution is key. So FE, I'm going to skip through this real fast. You said I'm not going to talk about it, so I'm talking about it quickly. The key thing here is, of course, knowing the conditions that you're analyzing, meaning the thermal conditions and loads. How is the part constrained? All these things are critical, okay? Defining the constraints, operating temperatures. And sometimes you go into, yeah, go ahead.
Sorry, back to the previous slide. Aluminum shrink, is that a standard, or do you factor that into kill design, aluminum shrink?
Aluminum shrinkage? What do you mean, for casting?
Only for casting.
For casting, yeah.
Yeah, only for casting.
Okay, I'm glad you asked the question. As a designer, I don't give two hoots about what you assign to the shrinkage for the tool, for the material. I don't care. Matter of fact, I'm a strong advocate of staying in my realm. You know, I know designers that tend to sort of get into the processes here. You know, like, I know guys that do mold flow analysis and do all these other things, but they're not making the parts. I believe that, you know, I do what I do, and then let that other guy do his thing, and we hopefully collaborate and have a meeting of the minds somewhere in the middle. Because when you start doing, imagine somebody coming into your house and telling you how to live. You're gonna be pretty annoyed. So it's the same thing in a profession. I mean, you wanna basically give the person on the other side that's doing his or her job the independence to do what they do best. That's my philosophy. So I don't add the shrinkage, I don't get involved in any of that. But I am concerned about the tolerances. Okay, I'm concerned about the end result, not the means to the end. Okay, so you know, sometimes when you go through these analyses, you do the analysis and you realize your part's not sufficient, so you have to go back and change it. You got to go through this repetitively. It's an iterative process. It's not necessarily a straight line solution. And you can experiment with different materials, different wall stocks. So the simulation is great, but I think again, you have to test it in the end to verify everything, because like I said, there are a lot of considerations that you really can't simulate. So I'm going to kind of skip over that a little bit, and I'm going to kind of go through these quickly. And I've discussed these. You got environment. I'll give you a good one. Vacuum and pressure. I remember looking at this application that somebody sent me a number of years ago. It was this huge, like 5-foot square profile, about 6 feet long. It's this huge tank. And they were going to pull a vacuum on it. It was to vacuum leaves or something. It was like a big vacuum cleaner, okay? And I think they had like about a 1/4-inch wall, and I said, what do you think? And I said, forget about it. I mean, could you know, if you ever made a pressure tank, I don't know if you've ever played around with pressure vessels, but even 2 PSI could be monumental. Think of 2 PSI over you know, 1,000 square inches. It's a lot of force, okay? So, the thing was a disaster. And plus they had all this crazy, there was a total lack of knowledge, in my opinion, of designing something. They wanted to make a vacuum seal with polyethylene with a, you know, a 1/4-inch wall, and it was like a pressure vessel. It just wouldn't work. It was totally impractical. There's no surface area to, you know, seal off, and plus the thing would deform like crazy. Anyway, really have to understand the materials and what you're doing. So chemical resistance, of course, you have to.
What do you recommend for a pressure tank?
What do I recommend? What do you mean?
What material
What-
to use to do
Well,
a pressure tank?
For a high-pressure vessel.
Well, it depends on how it's, that's a loaded question. I'll tell you why. I'm not trying to avoid it, but you can use polyethylene, you can use nylon, you can use polycarbonate. It doesn't matter. It's how you design it. Okay. So if you're using polyethylene, all right, which is common for rotational molding, you ask what grade and what resin. I can't. He's going to try to sell you his resins, but you know, you.
But you use polyethylene linear, or you would use a crosslink?
It's if you look at if you're designing it with, I'll answer your question indirectly. Let's say it's linear low density, okay? If you are designing it, you look